Heisenberg's Uncertainty Principle. Heisenberg's uncertainty principle is one of the most profound and important concepts in quantum mechanics. Introduced by Werner Heisenberg in 1927, this principle fundamentally challenges the classical notion that we can precisely measure the properties of a physical system without limitation. Specifically, the uncertainty principle states that certain pairs of physical properties, such as the position and momentum of a particle, cannot both be measured exactly at the same time. The more accurately one of these properties is determined, the less accurately the other can be known. This inherent limitation is not due to technological shortcomings but is a fundamental feature of nature itself. The mathematical expression of the uncertainty principle is commonly written as delta x delta p, greater than or equal to /2, where delta x represents the uncertainty in position, delta p represents the uncertainty in momentum, and h bar is the reduced Planck's constant, a very small number that plays a key role in quantum mechanics. This inequality shows that the product of the uncertainties in position and momentum cannot be smaller than a specific value, implying that perfect knowledge of both is impossible. If you know the position of a particle with high precision, very small delta x, the uncertainty in its momentum, delta p, must be large, and vice versa. The origins of the uncertainty principle lie in the wave-like nature of quantum particles. In classical mechanics, we think of particles as point-like objects with definite positions and velocities. However, in quantum mechanics, particles like electrons are described by wave functions, which provide a probability distribution for the particle's position and momentum. A particle's position is spread out over a range of possibilities, and the wave function gives the likelihood of finding the particle in a particular location or with a particular momentum. This probabilistic description reflects the intrinsic uncertainty in these properties. The wave-particle duality of matter is central to understanding the uncertainty principle. When a particle is localized or confined to a small region in space, its wave function becomes more concentrated, which increases the uncertainty in its momentum. Conversely, if a particle's momentum is well-defined, its wave function must be spread out over a larger area, leading to greater uncertainty in its position. This trade-off between position and momentum uncertainties is the essence of the uncertainty principle. To illustrate the concept, consider a simple example with light. Light behaves as both a particle, photon, and a wave. When you try to observe the position of a photon using a high-energy microscope, you need to use light with a very short wavelength, which corresponds to high energy and momentum. The high-energy photons interact strongly with the particle, disturbing its momentum. Therefore, while you may measure the photon's position precisely, the interaction changes its momentum, increasing the uncertainty in your knowledge of its momentum. On the other hand, using light with a longer wavelength to minimize the disturbance results in less accurate knowledge of the photon's position, as longer wavelengths provide less spatial resolution. The uncertainty principle is not merely a statement about the limitations of measurement instruments. It reveals a fundamental limit on the precision with which nature itself allows certain pairs of properties to be known. This is a stark departure from classical physics, where it was assumed that, in principle, every property of a system could be measured to arbitrary precision. In the quantum world, the uncertainty is not a result of disturbances caused by measurement but rather an inherent characteristic of quantum systems. The implications of the uncertainty principle are far-reaching. One of its most significant consequences is that it eliminates the possibility of determinism in quantum mechanics. In classical physics, if you know the initial conditions of a system, such as the position and velocity of a particle, you can, in theory, predict its future behavior with absolute certainty. However, the uncertainty principle means that even with complete knowledge of a system's quantum state, you cannot predict its future behavior with absolute precision. Instead, quantum mechanics provides only probabilities for different outcomes. This probabilistic nature of quantum mechanics contrasts sharply with the deterministic view of classical physics. The uncertainty principle also has profound effects in various physical phenomena. For example, it plays a crucial role in the stability of atoms. Electrons in an atom are confined to a small region around the nucleus, which implies that there is significant uncertainty in their momentum. This uncertainty prevents the electrons from collapsing into the nucleus, as classical physics might predict. Instead, the electrons remain in stable orbits, a result that is described by quantum mechanics and consistent with the uncertainty principle. Another consequence of the uncertainty principle is the phenomenon of quantum tunneling, where particles can pass through energy barriers that they would not be able to surmount according to classical physics. The uncertainty in a particle's momentum allows for the possibility that, for a brief moment, it has enough energy to tunnel through the barrier. Quantum tunneling is an important process in many areas of physics, including nuclear fusion in stars and the operation of certain electronic devices like tunnel diodes and transistors. The uncertainty principle also has implications for the vacuum of space. In classical physics, a vacuum is simply empty space, devoid of matter or energy. However, in quantum mechanics, the uncertainty principle implies that even in a vacuum, there are fluctuations in energy due to the uncertainty in the momentum and energy of particles. These fluctuations give rise to virtual particles, which briefly appear and then disappear, contributing to phenomena such as the Casimir effect and Hawking radiation from black holes. Philosophically, the uncertainty principle challenges traditional notions of reality. In classical physics, the properties of objects are considered to exist independently of observation. In quantum mechanics, however, the act of measurement affects the system, and the precise values of certain properties are not well defined until they are measured. This raises questions about the nature of reality and the role of the observer in the quantum world. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that physical properties do not exist in a definite state until they are observed, while other interpretations, like the many-worlds hypothesis, propose that all possible outcomes of a quantum measurement exist simultaneously in different branches of the universe.